Away.
All right, welcome back. Yeah, so let me continue a little bit what I was talking about yesterday. So I ended on a note where I talked about QCD. So let me just write up the Lagrangian again. All right, that's our Lagrangian. And we had SUNC times SUNF for the flavor. And then I said that this was a useful thing to consider because when you double copy the theory, it had one benefit, and that was in the case that you can, for example, if you set the mass to 0, I guess it could be, this is the mass of the quark, and then you're summing over the quarks, but you set the mass to 0, you consider d equals 4, and then you consider NF equals to -1, and it has the benefit of being allowing you to remove dilaton and axion. So let's just draw a picture of that. So say I want to compute, for example, 4.1 loop. So let's say I have 4 gravitons, and I want to do it in pure GR. I'm just going to draw one diagram, but you can imagine that you can do the same thing for the other diagram. Sorry, that's an H. These are H's, not N's. So the prescription here is that you essentially just start with pure Yang-Mills diagram, and I guess I should draw them curly. So this is just pure gluon here, so pure Yang-Mills. And assuming that color-kinematics duality has been satisfied, you can now square this diagram. But yeah, the issue is, of course, is there will be axions and dilatons propagating in the loop here. And so these are gluons. So you have to subtract out unwanted states. And the point is that you can very easily do that by including massless quark or fermion or whatever you want to call it that couples to the gluons. So you still have gluons here. But here you have a quark, which is massless. And then what you do is that you multiply with the same diagram, but you reverse the order. Sorry, you reverse the arrow. Sorry, wrong way. This screw cannot draw. Okay, so the opposite direction, and you multiply them together, and it's still going to be gluons. And as I say, it's important that you do that for the same loop momenta. So if you have some loop momenta here, L there, you have to make sure that you have the same loop momenta there, here, and here. So the arrow does not indicate the direction of the loop momenta, but just the direction of the helicity or chirality of the fermion. Yeah, so basically you're multiplying a chiral and anti-chiral fermion, and the product will be a scalar. In fact, there will be 2, so you have to put the factor 2 here. But that just means that I could have reversed this one and reversed that, but that's of course going to be the same thing. So this factor 2 basically takes into account the unwanted axion and dilaton contribution. And obviously, you can generalize this to higher loops, assuming that you can find the numerators that obey color-kinematics duality. But the strategy is always the same. Just compute your diagrams as if you were just doing QCD. But then when you do the double copy, you always take the massless limit, you anti-align this arrow, the fermionic arrow, and then you put a minus sign. So this could have been written as NF to the first power, and then there's still a factor of 2 because of, you know, the arrows can go both ways. So I could have written like that. So the fact that I put NF to be -1 gives me the fermionic minus sign. So obviously when you go to like 2 loops, you're gonna have, or 3 loops or whatever, you're gonna have some diagrams which have a single fermionic loop. You're gonna have some diagrams which have 2 fermionic loops. So the one which has single fermionic loop is gonna get a minus sign. The ones who have 2 are gonna get a plus sign. So you're basically adding and subtracting various diagrams. And at the end of the day, it should work out, and it gives the pure theory, the pure DR theory. Maybe a small comment related to that. You might not be happy by me calling that pure DR because I only have the metric. I only have the gravitons, whereas maybe a traditional DR person would say you also have to allow matter, right? I mean, you know, DR can have matter. So here, what I mean is that it's strictly the case where you have no matter. Because when you have matter, then you're still going to have axion dilaton contributions because the dilaton couples directly to the mass of the matter. So this doesn't give you pure GR in the context of matter, but if you have no matter, or if the matter is massless, then this gives the right prescription. And I should also say that if you're interested in supergravity, this construction here does generalize from many supergravities, so you can get many pure supergravities. So generalizes to many pure supergravities. And by pure, I mean that you only have the graviton plus its super partner, so that's the super multiplet, but you don't allow for additional matter beyond that. And I should say that although this construction here was in 4D, for the pure supergravities, you can actually do other dimensions as well. So this is, as far as I know, is for any dimension that the supergravity is defined in. Okay. Yeah, then a second remark related to the double copy of QCD is that recall that in the spectrum of the massive particle, the massive quark, there's also a massive Procca field, which I talked about last time. So you can, in fact, if this is the first application of double copy of QCD, here's the second application. So you can use QCD times QCD double copy. So this can be used to model classical scattering of a Kerr black hole up to spin quadrupole. Basically S squared. And that's because in this double copy between the quarks, we have a Procca field, a massive Procca field. We also have a massive scalar, but so let me just remind you of that. But the point is that we're interested in the Procca field because it's known that the Procca field, which is just a minimally coupled massive vector, should give the right interaction, at least to, you know, for the calculations that has been done in the literature so far. So for example, you can consider, for example, an interesting process is to do some Compton scattering in gravity, where you put the spin, you put the vector here, so basically spin 1, and you put the vector here, so this is also spin 1. And then you have to worry about whether you can take like a classical limit of this process, but people have figured out how to do that. And you can also, for example, so this is Compton, I guess, Compton. You can also do conservative two-to-two scattering. Let me just draw a picture, something like this, for example. So this would be this would be 3 PM, say, if you're working in a PM expansion. And here again, you would put maybe like a vector, massive proca, which is spin 1. And then you can do whatever you want on the other leg. And here, for example, here, you would need the precise structure of the Compton interaction. And I should point out, in this QCD times QCD double copy, there's a bunch of states, lots of states that you don't want. There was the axion, there was the B field, and all of that. So that you have to basically fix by always cutting these lines here, and then inserting graviton projectors. So you make sure that you're only propagating gravitons.
Henrik, I think there's questions in the audience.
Yeah. I can't hear. Oh, yeah. Actually, I was going to come to that later, but yes, you can obviously supersymmetrize QCD, and then you get supergravities when you do the double copy. Yeah, so I was very vague here. I'm just saying this generalizes to other theories, and then I will come to the other theories maybe later, or maybe not. Let's see, yeah. Yes? Yes? Sorry, what? Yeah. Yeah. Uh-huh. Yeah, you can do a linearized diff transformation here, diffusion transformation, and check that it is invariant on those, yeah. Yeah. Yep. Ah. Yeah. No, there's no other symmetries. Yeah. Oh yeah, maybe one thing I didn't spell out is what do you do when you have quarks? How do you implement Color-Kinematics Duality of quarks? Yeah, maybe I should have talked about that. But essentially, it's straightforward. That's kind of why I forgot about it. But in addition to having the Jacobi, you of course also have the fundamental generators, so it's basically the defining property of your Lie group. So this also has to be imposed, and this diagrammatically, this just means that you have, if you have this diagram, and then you subtract, so you subtract the cross diagrams, then this has to be equal to this diagram kinematically. Well, it's both for color. If this was color diagrams, you have to impose this identity, or if it's kinematic diagrams, you have to impose this identity. And you don't impose, you also have to consider the case where you have this diagram, but there's no Jacobi or fundamental Lie algebra identity. This one is happy by itself. It's actually gauge invariant. So you can, yeah, that's how you implement Color-Kinematics Duality. In addition to the Jacobi, you have this identity. And this one, of course, is not really relevant here, but indeed there is this identity. So essentially, when you permute these two guys and subtract them, you're going to get a triangle. And if you do it twice, you're going to get a bubble. Essentially, the diagrams that David talked about earlier today.
Henrik?
Yeah.
Just then continue on that. So in the adjoint, you replace the CIs by the NIs. And here, how does it work to actually do the double copy? With
Yeah,
the
it's the same
quarks?
prescription. Just replace the color factor by the kinematic factors. Yeah, that's always the prescription. Yeah.
Always the same thing. Okay.
Yeah.
And
yeah.
you can also mix different kind of kinematic factors, like NITIL does.
Yeah, you can formulate the double copy in various ways, but the most convenient way to formulate it is say that you make sure that your color factors and numerators are aligned, satisfying the same algebraic relations. When that's true, you do make the replacement, right? So that what I just said, it doesn't care about which representation you're in or any details, right? So that formulation is very convenient, right? Yeah.
Okay.
Yep.
Thanks.
You might, okay, maybe a follow-up to that. You can also ask about, does the KLT formula still exist for fundamental quarks? And the answer is no. It does exist in the simplest case where you have like a single quark line. But when you have more than one quark line, for example, a tree level, then you have to basically start modifying the KLT formula. But from the point of view of numerators and color factors, it stays the same, right? So that's why that formulation is more convenient. Okay, so then I was just drawing some diagrams here. The last one I was going to do, so this was conservative, this is Compton, this is radiation. So these are basically the processes that people are mostly interested in amplitudes community. So you can have radiation here. And then you can put some vector field here, which is basically modeling your spin 1 black hole. And you can do whatever you want on the other one. I'm surprised I haven't gotten a questions so far, because some of you might be worried about what I just did. So we have this additional field here, right? So you might be worried that maybe inside this Compton, I'm actually going to have a scalar propagating. So this is not what people usually consider when they do Compton scattering. Like usually when you consider Compton scattering, you only want to have spin 1 everywhere. But it turns out that there is actually no allowed amplitude that transitions from spin 1 to spin 0. So I'm actually going to leave that as a homework for you guys. So homework, argue that spin magnitude. And here, you can take this word to mean the quantum spin magnitude. So at swing magnitude transitions, not allowed. And maybe to be very specific, let me talk about the specific amplitude. So this guy where you have a bunch of H, sorry, my H looks like N, sorry. And here you have S equals 1, S equals 1. So given that I fix my external states to be spin 1, gravitons, I'm never going to have a scalar in the middle. And so the simple situation where this could happen is that if you have a process where you're allowed to go from spin 1 to spin 0, then that obviously would contribute to this process. But what my claim is that this is not allowed. So you have to say that this is 0. And my homework is, can you make the argument why that's a 0? And let me give you a hint. Guess the Lagrangian interaction. And then rule it out. What I mean by that is, instead of looking up what this interaction could be, just write down whatever you think it is, and then you say, no, not reasonable. All right. Now I should say that this is probably not, doing QCD times QCD is probably not the best way of doing these calculations, but since this conference and school is called QCD means gravity, I figured that I should point out that you could do QCD times QCD to do a Kerr black hole up to spin squared. Yeah. What? This here? No. I think you can write down things which are Lorentz invariant. But you might still be unhappy by how it looks like, yeah. I mean, for example, if you think of if you think of classical gravity, you probably wouldn't be very happy to write down like a classical world line that where spin is changing here, and so there's something wrong about this process, right? All right. Okay, so I guess that was just the end of last lecture. So now actually I want to switch gears and talk about, rather than the double copy, I want to talk about theories that satisfies color-kinematics duality. Because in my previous lectures, I pretty much did not talk about, I did not specify the theory, or if I did specify the theory, I was saying something vague, like, yeah, my Yang-Mills. Well, then I did talk about Chern-Simons and so on, but let's try to be a bit more systematic. So list of theories that satisfy, and let me put that in quotation mark, color-kinematics duality. So the reason I put it in quotation marks is that this list is incomplete in the sense that we don't have proofs for what I'm going to say, so we just have partial evidence, right? So so the first one, and maybe the most important one, is just to think about Yang-Mills in so let's call it Yang-Mills D, because this is in D dimensions. And the reason why we think Yang-Mills in D dimensions satisfies color-kinematics duality is because the numerators are known. So tree level are explicitly known. To any multiplicity. Multiplicity. So basically it's a constructive proof. And now I should also be clear what I mean by numerators. What I really mean is nice numerators. So they are local. They're local, meaning that they have no poles. They're just polynomials. Just polynomials in momenta and polarization. And have the right permutation symmetry. Or let's actually, I gave it a name before, so I guess I should use the automorphism, correct automorphisms. Yes. I was hesitating there for a second because the work I'm thinking of, which is by Fei Teng and collaborators, they wrote down some numerators which initially did not have the correct automorphism identities. But of course, since these are local and happy objects, you can always just symmetrize. You can just like brute force symmetrize. So therefore, I say it's correct. Okay. The reason I'm specifying here because several years earlier, people wrote down numerators which were function of the tree-level amplitudes, and they basically did that by imposing or doing the pseudo-inverse of this propagator matrix. But that I feel like that's it's a bit of a cheat because now you just go to a specific gauge sort of say, and that's not very pretty. You could have non-localities and all of these issues. So if we take the best possible numerators, these are the ones we should look for, and so they are known at tree level. And I should say that this was obtained using CHY formalism. And as I said, it was I forget who the complete list of authors were, but at some later work, there's a paper by Fei Teng and Alex Edison. Which I think they still have the best representation of Yang-Mills numerators. Okay, so that's basically the status of Yang-Mills in D dimensions. And then we can talk about what about Yang-Mills in some specific dimension. So let's talk about Yang-Mills 2, so in D equals 2. Not too long ago, I think it was even this year, the kinematic algebra was actually constructed. So kinematic algebra is known. Don't ask me exactly what the kinematic algebra is in this case, because it was formulated in this BV language, and I get just confused by opening it up. So, but these guys are very good. One of them is my former student, Mar Ben Shahar. So I think we can declare that Yang-Mills in 2 dimensions is known, and presumably also to all loop orders. But you should read the paper yourself. That said, there's no particles in 2 dimensions, right? So this is a topological theory, right? Then there's yeah, I think they were not sure. I mean, it's a bit hard to read off because it's a topological theory, so the double copy is also topological. I think they're still doing research on that, so maybe I shouldn't spoil what they told me at some point. Yeah, maybe you should. Hope a paper will come out at some point. Yeah. Yeah. Say again. Yeah. You're asking if I'm claiming that? Sorry, what? Sorry, can you? I couldn't hear the beginning of the question. Oh, you're saying if I double copy a topological theory, will it always be topological? I'm not sure. I mean, if you double copy a theory which has no amplitude, then most likely the double copy will also have no amplitudes, and a reasonable guess why it doesn't have amplitudes is because it's topological. But I'm not sure if that's a proof. That's more like a hint that the double copy is topological. And then a second thing you can do is that you can double copy a topological theory with a non-topological one, and then you can ask what you get. And I think the answer is that it doesn't have to be topological, right? It can have propagating degrees of freedom. Yeah. All right, so the next one, which I probably should mention because it was historically important, is self-dual Yang-Mills in 4-dimension. And this is actually not a consistent theory, but it's a toy model that people like to work with. So this is a theory where the field strength is equal to the dual field strength under Hodge duality. And essentially what happens when you impose this constraint is that only one of the helicities of 4-dimensional Yang-Mills is propagating, and that's not consistent with CPT. So this theory breaks CPT badly, but it's still an interesting theory. And there it was, this was actually the first kinematic algebra that people identified in the context of Color-Kinematics Duality. So this gives area preserving diffeomorphism. The reason why it's area preserving diffeomorphism is because you can, in some sense, think of this as being like a 2-dimensional theory, even though I said it's 4-dimensional. But you know, there's a certain way of thinking of it in the complex plane, such that it becomes 2-dimensional. Yeah. 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 So you can, yes, indeed. So you can. It turns out that you can compute off-shell stuff at tree level, but if you compute on-shell stuff at tree level, it's 0. But then you go to one loop, and it turns out that at one loop there is an amplitude. So this theory only has a one-loop amplitude. It's a very funny theory. No tree-level amplitude, no higher loop, just one loop. And the double copy is self-dual gravity. Yeah, so maybe I should write that here. So double copy is self-dual gravity, GR. You might, I don't know, how many know what self-dual gravity is? Yeah, so it's basically just the same. It's the same. you take the Riemann tensor, and then you impose that is equal to its dual. Let's just call the dual tilde. You're basically you're dualizing two of these indices, basically. Yeah, that's a well-known thing. So again, it has the same property. It doesn't respect CPT. It only has one of the helicities of the graviton propagating. It only has one loop amplitude. All of these things were known, of course, before people realized that they were connected via double copy. Okay. Okay, so that exhausts what I was going to say about pure Yang-Mills. So now let's talk about things which is not pure. So let's talk about Yang-Mills scalar. So this is a common name that people use, at least recently in the literature. And I think what they really mean here, although I think different authors could mean different things, is that this is actually pure Yang-Mills, but you have dimensionally reduced it. So it's pure Yang-Mills plus dimensional reduction. And then, of course, you're going to get a theory which has both scalars and gluon. So you're going to get this thing here. And everything is in the adjoint. So that's one big trace over everything. So it's just pure Yang-Mills, but now you have basically let it have like a lower dimensional gauge field, and then external space gauge field and internal space scalar, right? So if you just do this replacement in your pure theory, and then you remove anything that's not consistent with the indices, then you get that Lagrangian. And because it's secretly pure Yang-Mills, you can actually use the same numerators. So these numerators that worked here, they will also work for that theory. Okay. Now, if we take this theory a step further, we can do something interesting here. So now we have a bunch of scalars. So we can give the scalars a vev. And we get essentially spontaneous symmetry breaking. So we can do Yang-Mills scalar with spontaneous symmetry breaking. Which people usually call SSB. Okay, and to be specific here, of course, you can do symmetry breaking in many different ways. But what you kind of want to do here is that you want to look, you want to look at places where the potential vanish. So the potential, this is a potential here. So the potential vanish when this vev is abelian, right? Because that's a commutator. So whenever the vev is abelian, basically a bunch of U1s, then the vev will vanish. Then the potential will vanish. And so this has many flat directions. So I think I would maybe say this is like a flat Higgs potential. Well, this potential is not flat, but you're basically have many flat directions. And this basically means that Higgs is massless. Unlike what we are used to from the standard model. I'm just saying that because I don't want to give the false impression that we're actually doing the standard model here. And sometimes this is also called the Coulomb branch. So the Coulomb branch, well, it has something to do with Coulomb potentials, but the point is that if you have scalars in the adjoint, which you have here, then you're naturally led to the Coulomb branch. So this is basically adjoint scalars. Whereas if you have fundamental scalars, then people typically talk about the Higgs branch. So that's not what I'm talking about. Okay. Yeah, let's see. So the reason I should say why it satisfies Color-Kinematics Duality. It's because this is actually secretly related to Kaluza-Klein. Kaluza-Klein, so I'm gonna abbreviate this as KK, not to be confused with Kleist-Koef. So this is secretly related to Kaluza-Klein Yang-Mills, specifically the numerators of this theory. Okay, so let's put that on the list next. So Kaluza-Klein Yang-Mills satisfies Color-Kinematics Duality. So Kaluza-Klein, as you know, is that you compactify your theory on some compact space. So in this case, let's pick the simplest one, which is a toroidal compactification. So the N torus And then what you can do is that you can actually just take your pure Yang-Mills that lives in higher dimension, and you can take the momenta to simply be, it has some external space momenta and then some internal space momenta, which I'm just going to call mi. So basically, this is a space-time vector, Lorentz vector. This is some SON vector in the internal space, because the symmetries of the N torus is basically SON. Okay, and so that's what you do with the momenta. The polarization, similarly, you just decompose it into external space. Sorry, maybe I used curly. External space polarization and then internal space. Let's just call let's call this polarization of the scalars the same as the scalars. Obviously, it's not a field, but for lack of notational imagination, I'm just going to call the polarization of the scalars the same as the scalars themselves. Okay, so if you just take this prescription, just plug it in to these numerators, it's going to give you Kaluza-Klein Yang-Mills on an N torus. It's super trivial. You don't have to do any work at all. So that means that same numerators will work for this theory. And what's interesting about Kaluza-Klein is that you can sort of think of this as some kind of spontaneous symmetry breaking. Let's put quotation mark around spontaneous, because it doesn't seem very spontaneous to me. I mean, I just did it, but let's call it spontaneous symmetry breaking of the Lorentz group. So if you start from SO1, D minus 1, so that's your original Lorentz group, then you can just break it down to SO1, D minus 1 times SON. And here, D, my capital D, is just little d plus n. That's basically, that's one way to think of this toroidal compactification, is that I just make it like that. And so you see that seems quite similar to how we break gauge groups. So in fact, we can think of Kaluza-Klein Yang-Mills as having a breaking in the kinematic factor, but not in the color factor. So if you think of it as color times kinematics, then we're just saying that Kaluza-Klein is just breaking the kinematic part. But it doesn't do anything to the color. The color just stays as it is. And then as I said, you can relate this Kaluza-Klein Yang-Mills to this spontaneous symmetry breaking on the Coulomb branch specifically. And you can think of that as breaking both color and kinematics. In some intricate way. Of course, I'm not reviewing the Higgs mechanism or whatever, but I'm just pointing out that there is a specific interpretation where you can think of it as breaking both color and kinematics. And then my statement is that these two things are somehow related. And the relation is that you can go from the numerators of this theory to the numerators of that theory using a consistent truncation. So that's, yeah. I'm not gonna quite explain what consistent truncation means, but I'm gonna give some examples. But it's a very established term in the literature, so everybody uses consistent truncation in the same way. So let's just give an example. So let's assume that we're on the 1 torus. And then you might know that this Kaluza-Klein spectrum is going to be like an infinite sequence of equally spaced massive particles. So I'm just going to consider the mass here. So for example, we're always going to have a massless particle when you have compactified on a circle. Sorry, what am I doing this right? Sorry, this is a circle. I was confused. Yeah. So the 1 torus is circle, yes. I'm confused. So we're on a circle, or a 1 torus, and I was saying that we always have particles of 0 mass, but then we might also have a particle of mass m, and then we can have 2m, and then we can have 3m, and so on. And likewise, it's also convenient to extend the masses to negative directions. So we're going to have minus m, minus 2m, minus 3m, and so on, all the way to minus infinity. So this is S. Okay, so now, of course, this infinite spectrum is not going to be present in the spontaneous symmetry breaking. So we have to make a truncation here. We have to assign which states to keep, and then do something additional to that. So let's think about how do we typically break a gauge group? Well, we have some SU N1 plus N2, and then we go to SU N1 times SU N2, and then times a U1. That's also a U1 coming out. So that's how we typically break it, and you can imagine that pictorially, that we have our joint matrix. So this is N1 plus N2. Same one here, so N1 plus N2. So we can place all the generators in this N1 plus N2 square matrix, and we can put all the unbroken fields on the diagonal, and then we put the broken fields on the off diagonal. So I chose this notation. So A here is just unbroken gauge fields, and W are basically broken directions, so basically the W bosons. And so now we have to basically assign masses to this particle according to this infinite spectrum here. And the obvious choice is, of course, to assign that the gauge field has to be massless, or the unbroken gauge field has to be massless. And then for this massive guy, we just say that that's the W boson, and this one is the W bar boson, the conjugate. And then we just say that this one goes to 0. This, we don't want those ones. So that's the truncation we're doing. And now the word consistent here is that you have to check that this is consistent, in the sense that when you scatter these particles, they will always remain in this subsector. They will never leave this subsector. And that's the reason why they never leave this subsector, is because we have correlated the color breaking with the kinematic breaking. They're correlated, and they will always stay correlated. Okay, and you can do it more fancy. So let me maybe do one more example. So if you have a more advanced breaking, such as SU N1 plus N2 plus N3, which which we're going to break into 3 parts. Maybe I write it over here. So we break it into SUN1 times SUN2 times SUN3, and now you're going to have U1 squared. So for this one, I guess I should have used a different color. For this one, you're going to get like a 3 by 3 blocks. So these are blocks. These are not. It's not a 3 by 3 matrix. It's just blocks. So again, we're going to put the unbroken one on the diagonal. Let me also give them a label: 1, 2, 3. This is just for the 3 different gauge groups. And then on the off diagonal, we put W12, W13, W23, and here we put W12 bar, W13 bar, W23 bar. And now one consistent truncation you can do is again that you put all the A's here, so all the massless, unbroken gauge fields here. Then you put, for example, W12 here, also W23. But now you can put something here, so that's W13. And here you put W12 bar, W23 bar, and here you put W13 bar. And for the rest, you just put 0. So that's one way to do it, and this will also be consistent. So now you have W bosons of different masses. This one will be twice as massive as this guy, but you still have degenerate masses, right? So I guess I'm gonna give you homework. Homework. Maybe this chalk is not so good. Homework. Consider the true torus, so the T2 torus spectrum. And find a consistent truncation such that masses of W12, W123, and W13 are different. Maybe it's not obvious what to do, but let me just give you maybe some hints here. Notice that the mass spectrum here, so the masses of Wij is equal to M times I minus J. Or maybe the other way around. Yes, I think it's the other way around. J minus I. Sorry, minus I. And this is, of course, minus Wij bar. I don't know, that's a hint. Meaning that's a relation between these numbers and the masses. Okay. And also, maybe to check what's consistent, what you should really do is that you should check that if you have 3 W bosons, so W12, W23, W31, whatever. Then never mind. I guess the ordering here matters here, but I think this is fine. Yeah. So if you have 3 W bosons, what you should make sure is that this mass vector that we introduced at some point, this mass vector has to respect momentum conservation. So so if we call this thing M31, M23, and this thing is M12, you better have that M12 plus M23 plus M31 is equal to 0. Anyhow, that's all the hints. You have to do it yourself. Any questions about that? Yep. Mm. Sorry, what? Oh, if you can put all of them to be the same? Yeah, you can put them all to be the same. Or sorry, well, maybe not. Well, you have to be careful. You still need to, like if you have 3 W bosons, then you need to make sure that it respects this mass conservation. So yes, you can make them all the same, but you have to do it by some trickery. So it's like non-trivial. And you cannot do it on the circle, but you can do it. You can do it on the 2 torus, but you have to pick very particular mass vectors to do that, I guess. Yeah. And if you, another thing is if you assign 0 masses, of course, then you're not really breaking the theory. So then, so 0 masses are kind of not allowed for the W's. Okay. Any other questions? Yeah. Second? No, the W bar is just a complex conjugate. Yeah. Why shouldn't it be physical? It's just a complex conjugate. So whenever you break, oh no. What matters is the mass squared. It doesn't matter what the sign of the mass is. Yeah, I mean the sign of the mass is irrelevant. But by convention, we always take masses to be positive. But if you check pretty much any physical quantity that you compute, it's always mass squared. I think the only exception to that rule is that if you have fermions, then you have a Lagrangian which is linear in mass. But you also know that for fermions there is some sign ambiguity. So in fact, if you flip the sign of the mass and the direct Lagrangian, it's fine. That's just like a different phase choice. So yeah, negative masses are fine as long as you're as long as you know what you're doing. Right? So here it's just it's just a tool to get the right answer. But in the Lagrangian, which I guess I haven't given the Lagrangian because it's a quite ugly beast. But in that Lagrangian, they will only depend on m squared. So only m squared will appear in the Lagrangian. So you can, the minus m's are fine, yeah. Yeah. Any other questions? Yeah. 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 So obviously the more internal dimensions you have, the more freedom you have in assigning these mass vectors and then indirectly assigning the mass, right? Oh yeah, and I didn't say that. Maybe I should have said that here. That of course the true mass, let's call it m absolute, because it's supposed to be positive. This of course is mi times mi, where you contract these indices with the Euclidean metric, and then you take the square root. And I should also say, unfortunately, because most physicists who do amplitudes work with the mostly minus signature, you have to put a minus sign there as well, because this dot product is minus. But whatever, this is just a quirk of the mostly minus signature. Okay. Any other questions? How am I doing on time? I'm minus. Wow. Okay. I thought I was gonna run out of stuff to say. Yeah, let's see. Do I need to say something else? Oh yes, yeah. Okay, yes, I still have half an hour. Yeah. No, sorry, I also got confused. I should not start on half hours. That's confusing. Okay. Yes. Okay. Good. Yes, I think that's what I was gonna say about spontaneous symmetry breaking. And yeah, I made a long story here, and the short story is that you can use the same numerators. Those numerators works, you know. So you don't have to write down the Lagrangian here. That's just a big mess. Just use the pure Yang-Mills numerators. Okay. Yes. So that kind of concludes all the things that you can get from this pure Yang-Mills numerators. You get all of that for free. Let's talk about something else that we kind of get for free, but not really. You know, there's this magic words that people use. You know, let's supersymmetrize, right? Let's supersymmetrize. So we can just supersymmetrize everything that I said. So supersymmetrize all of the above. And of course, you have to do it carefully, right? You know, sometimes you can supersymmetrize, sometimes you cannot. But in the cases you can supersymmetrize, we expect that color-kinematics duality holds. Now, if you want to get the supersymmetric numerators from the bosonic numerators, well, that's hard work. But in principle, it should be possible to do it. But I don't even think there are any formulas in the literature that does that. But in principle, they should be related. Okay. So this means that we can then also declare n equals 4 super Yang-Mills to obey color-kinematics duality at tree level, essentially because the tree level amplitudes are related to Yang-Mills by Susy-Ward identities. The Susy-Ward identities are sometimes a bit hard to use, unless you're at low multiplicity. But you know, they should exist. You should be able to use them to solve for amplitudes and numerators more generally. Amplitudes, maybe numerators is harder. And I'm not going to talk about it. I mean, David mentioned it in his talk, and that's what I'm going to do here. I'm just going to mention it. I'm not going to talk about the Susy-Ward identities. But anyhow, so n equals 4 is the most supersymmetric theory, and this, of course, lives in 4 dimensions, 4D. You can also lift it to higher dimension, but then it changes name, so that's a bit confusing. So you can also do it, for example, you can do let me put it here. Well, this is also known by n equals 1 sim in 10D, and it's also known by n equals 1,1 in 6D. So it's kind of a constant annoyance that you have to change the name or whatever. But it has many names when you uplift it to higher dimensions. So all of those should also work. But if we stay in 4D, of course, then we can actually truncate the supersymmetry of this theory. So that's also a consistent truncation. And so you can truncate it to n equals 1 and 2 super Yang-Mills in 4D. And this one you can also truncate to n equals 1, 0, but let me not talk about that. So this follows by either by Ward identities or Susy truncation. Susy consistent truncation. So another way to say what consistent truncation is that you need to make sure that the particle that you're truncating away can only be pair produced, because that way, if you disallow them on external states, then at tree level they can never be produced because they have to be produced in pairs. So that's usually what consistent truncation is referring to. Okay, and I guess I'm gonna talk about the supergravity later, but for now, let me just say some more gauge theories. Well, actually, the next one is not a gauge theory, but let's put it here anyhow. So that's the bi-adjoint. Bi-adjoint scalar, which I already mentioned, so I'm not gonna say anything more about it. Let's just put it on the list. The only thing is that since this bi-adjoint scalar obeys color-kinematics duality and Yang-Mills satisfies color-kinematics duality, you can ask whether they can live together as one theory. That means can you couple the bi-adjoint scalar to Yang-Mills? And the answer is yes. And I usually call this theory Yang-Mills plus phi cubed, because now you have a Yang-Mills interactions and you have the phi cube interactions of bi-adjoint scalar. I think other people call it Yang-Mills plus BAS. So that's like two names which are floating in the literature. Just be aware. Now, I don't think I have a simple argument why this works. I mean, you can kind of squint your eyes and say, yeah, it kind of works, because if I only compute amplitudes in the bi-adjoint scalar, it works. If I only have states in the bi-adjoint scalar sector, it works. And if I only have states in the Yang-Mills sector, it works. But I guess the non-trivial thing is when you have states which are both gluons and scalars, why does it work? I don't know. I mean, it just works. I'm not sure if the numerators are known for this case. They are in some sense related to the pure Yang-Mills numerators, but they're not simply related. So I'm not sure if they actually exist in general. So I guess somebody should write a paper where they figure out what these numerators are. If you had the numerators of this theory, then you can always go back to Yang-Mills. Essentially, the way you would do it is that you just take the bi-adjoint scalars to be soft. If you take them to be soft, you should go back to Yang-Mills numerators. Yeah. This just means that we couple them to each other, and there's an obvious coupling, which is just covariantize the derivative of the bi-adjoint scalar. Yeah. So let me do it schematically, right? So it's just f squared plus d mu phi squared plus lambda phi cube, right? And then you have to put the bi-adjoint indices in yourself. So you see that this is the bi-adjoint theory, and this is Yang-Mills and whatever. Yeah. Okay. Yes. Okay. You might think that this theory looks a bit artificial because, you know, we have Yang-Mills in nature, but we don't have bi-adjoint scalars in nature. But it turns out that this theory is very important for the double copy, because in the double copy you will actually get something that does exist in nature, which is essentially how to couple. Yeah, maybe I should explain it already now. So if you double copy Yang-Mills plus phi cubed with Yang-Mills, what you get is is there a name for that? Einstein was just I was blanking. And I think I even have a paper where I wrote it the other way around, Yang-Mills, Einstein. So that's, that's I don't know. I don't know which one is the correct order. I think most people write it like this, but since I have a paper that writes it like that, I claim priority. Okay, yeah, and so this is basically just the Yang-Mills Lagrangian. It's just R, well, square root of minus G plus F mu nu trace. And of course here you contract with the metric, so the gravity couples to the F. And there could be additional stuff. There could still be the dilaton and the axion, but so plot plus dot dot dot. And this is the real world, because of course we have gravity and we have Yang-Mills. So, okay. Yeah. Oh, if you do it on both sides, well, then you get some not physical theory. Well, basically, what you get is, okay. So maybe I should here I should state what is the bi-joint with the bi-joint, right? So what is BAS times BAS? And I think many people in the audience knows what it is. It's BAS. So it's essentially the bi-joint scalar is the identity operator, or another way to think of it, this thing is the inverse of this product. Like this is one. And so now you can figure out what you get, right? You see why you see why we got Einstein Yang-Mills here, right? Because you get gravity from here, then you get Yang-Mills from here, right? So essentially, if you put Yang-Mills plus phi cubed twice, then you get 2 Yang-Mills sectors, and then you get also a bi-joint scalar sector. Yeah. Okay. Any other questions? All right. So yeah. Okay. So I'm talking about scalars. So let's talk about more scalars. So we said the nonlinear sigma model, which I discussed last time, but let's discuss why it works. So it turns out that this nonlinear sigma model is secretly related to Yang-Mills via spontaneous symmetry breaking. So this is related to spontaneous symmetry breaking of Yang-Mills. Specifically, people, of course, identify the scalar of the linear sigma model with the pion of QCD. But I mean, there is some argument that goes roughly like this: is that you can let's think of maybe I do it over here, and I might get the details wrong, but if somebody notices it, let me know. So essentially, let's consider this gauge field. U dagger d mu u. And does anybody recognize that formula? That's a gauge transformation, right? So this is a gauge. This is a pure gauge field. It's pure gauge, pure garbage. Because, or is that the right way to think? Yeah, I think it's the right thing to think with, yeah. But let's consider this field. And I think the claim is that if you insert this field into the field strength, then it vanishes. Let me know if you agree with that. It should vanish if I insert it in the field strength. But if I insert it in a mass term, let's say the gauge field has a mass term, and that's also a trace here, right? Then of course it's not gonna vanish, right? So then you're gonna get trace u dagger d mu u u dagger d mu u, and then also m And that's typically over 2 here, so m squared over 2. And now you might see that this looks a lot like the nonlinear sigma model that I presented last lecture. I guess you just have to do some integration by parts and so on. Yeah, long story short, you can compute amplitudes in the nonlinear sigma models by using recycling Yang-Mills numerators. And I think this was first demonstrated by CHY. I think CHY gave a formula. So they used the CHY language, which I'm not going to explain, but they just show how, what's the operations that you need to do to map a Yang-Mills expression into a nonlinear sigma model expression. And I'm not going to review it here because, well, I'm probably going to get it wrong because I don't have it in my notes, and we're kind of short on time. But if you want to ask me privately or this afternoon, I can try to explain it then. Okay. Okay, so then the next list here is something we already discussed. So that's, of course, super Yang-Mills. Well, we discussed Yang-Mills plus massive matter, so fundamental matter. Which we often think of as being quarks, but they could also be scalars. But in the case that there are quarks, you're going to get S QCD. So it could be supersymmetric QCD or not supersymmetric QCD. And specifically, it can only be n equals 1 to S QCD or n equals 0 QCD, which is just the usual QCD. You cannot have n equals 4 QCD if you have fundamental matter. And here, I don't actually have an argument why this works. I don't have any way to relate it to the original numerators. So here, we just checked it up to 8 points at tree level. And we also have done various calculations at loop level. We had done up to 2 loops in this series. Well, in both in n equals 1 and n equals 2, we have done a calculation up to 2 loops. It satisfies Color-Kinematics Duality. But I do think there's a severe lack of proofs in this case. So I'm not, I wouldn't bet my fortune on that this always works, but it does feel like it works because there's a lot of non-trivial things that works. Yes, next thing I want to mention here is something that people have called Z theory. Which is just a strange name it's a strange name for something that's not a theory. But there's an object that was labeled as follows. So there's an object labeled by Z, and it depends on 2 permutations. And it has an explicit formula. Let's see if I can write that. So it's an integral dz it's a product. It's a product dz I from 1 to n over volume of SL to Z. Another product up to n Zij 2 alpha prime Sij S12 Z12 Z23 Zn1 permutation of that, and then an integral over this domain. Okay. So some of you probably recognize what I wrote down. So this is obviously a stringy object. It depends on alpha prime, which is the string coupling. It depends on the Mandelstam's. It depends on this coordinate z, which is basically coordinates on the Riemann sphere, or sorry, in this case, it's actually on the annulus, so on the disk. These are actually real. So z is real, but it looks like they're complex, but never mind. This is the Koper-Nielsen factor. This factor here, sometimes people call Park-Taylor, although it has nothing to do with Park-Taylor, so I don't know why it's called that. And so this goes under the name Z theory, simply because it was called Z. It's something that you can think of as a string amplitude, but it's not a string amplitude of either the bosonic string nor of the superstring, because first of all, it's an object of massless scalars and has no supersymmetry. So it's a kind of an auxiliary object. And I should also say that it depends on the sigma, which I forgot to write. So there's a sigma, which is basically a permutation. So this permutation allows you to permute this contour that you're integrating over, and this permutation allows you to permute the indices of these labels. And yeah, it's called Z theory. It computes things which looks like amplitude, and all of those amplitudes obeys Color-Kinematics duality. It obeys Color-Kinematics duality in this color ordering. So this is a color ordering. So in this color ordering, it obeys Color-Kinematics duality. In the other color ordering, it does not obey Color-Kinematics duality, but it obeys something called monodromy relations. Which is a stringy version of the BCA relations. Anyhow, so this is a very nice object. And the point of this object is that it is actually a building block to compute physical, not physical, but true string amplitudes. So let me actually explain that here. So if you take Z theory, and double copy it with super Yang-Mills, then what you get is actually the superstring, well, let's say open superstring. At the lowest order in the string coupling expansion. So open string, superstring amplitude. And it's important here that you're actually double copying this color ordering that obeys Color-Kinematics duality and not the other one. So the other one is actually related to the Shane-Payton factor that you need to address your string amplitudes with. You can also, what else can you do? You can also get bosonic string amplitudes from this, but that's a bit more complicated, so maybe I should not do it right now. But it's important to know that this object exists, but it's a little bit weird object, so some string theorists might complain about it. But it is actually related to something you may be aware of. So it turns out that if you set the two orderings to be the same, so if you set it to be sigma, sigma, then you can actually think of it as the Veneziano amplitude. And I'm not sure if I spelled the name right, but yeah, Veneziano amplitude. Not the Veneziano amplitude that people like to work with for tachyons, but for massless scalars. So it turns out that there's a Veneziano amplitude that has a free intercept. It's called the intercept, and you can choose it freely. And for the particular choice where you get massless scalars, this is the amplitude. And that's, of course, not what people these days work with. They actually work with the massive tachyons. But never mind. You can ask Thales about this. Am I out of time? Almost. Was I going to say anything more? Maybe let's say just two more cases. One of them we already discussed yesterday, which was just Chern-Simons theory. So let's just put here Chern-Simons theory. And I'm not going to say anything more about that. Well, I could say that there's an extension of this case, which we call Gay-Otto-Witten. N equals 4 Chern-Simons matter theory. So that's people write it like that. So that one also seems to work. That also seems to satisfy color-kinematics duality. Although we don't have a kinematic algebra for this one, only for the pure Chern-Simons theory. And then you can also add higher derivative, corrections to Yang-Mills. I don't know why you want to do that, but you can. So for example, you can consider Yang-Mills plus f cubed. So this is a f cube operator. I think David already mentioned f cubed as an interesting object. Though I should say that this does satisfy color-kinematics duality, but only to linear order in this f cubed perturbation. So if we say that this is a perturbation, then only to linear order in lambda. But for any amplitude, as long as it's linear in this perturbation, it obeys color-kinematics duality. And if you want, you can also find a nonlinear completion, which I did together with Thales, but I'm not going to talk about it today. So I guess that's all I was going to say. So feel free to ask me questions. And if I forgot something on the list, which I probably did, you can also let me know about that. Thanks.
Okay, more questions? Yes.